to the last session of today. And we are very happy to have Oleg Lisovvy, which is going to talk about Painlevé tau function and irregular conformal blocks.
Thank you. So I would like to start by thanking Alessandro and Giulio for organizing this workshop and for giving me the opportunity to speak here. My talk will be like very elementary. So basically I would like to review some recent and not so recent developments about irregular conformal blocks and Painlevé tau functions. So my main example will be the first Painlevé equation, which is this second order nonlinear differential equation. So t is the independent variable. So typographically, this is the simplest of all Painlevé equations. And like for the other Painlevé equations, the general solution of this is transcendental. Moreover, so in this equation you have no parameters, and actually it has no classical solutions at all. That is, not even a single solution is expressible in terms of classical functions. So this is bad news. The good news is that, like the other Painlevé equations, this has Painlevé property.
What do you call by simplest solution?
Simplest?
Even a single solution?
Not a single solution. Yeah. So basically, in other equations, you have you can sometimes put some constraints on parameters or on the initial conditions, algebraic or special function solution. And in this case, you don't have any of this. Okay, so you have this Painlevé property of absence of movable branch points. So basically this means that the function q of t, so the general solution of this equation, is meromorphic in the entire complex plane. And meromorphic, it can only have simple poles. So you have something like this, q as t goes to the position of such a movable pole. So you have something like 1 over t minus t naught squared plus some other terms. So t naught, you can think of it as being one of the integration constants for the equation. And the second integration constant will appear somewhere at order 4. And if you want, you can compute this series expansion about a movable pole up to any order just using your differential equation. Okay. Then the next nice thing about this Painlevé one is its Hamiltonian form. So of course we can write it as an autonomous Hamiltonian system. So P prime is equal to minus dH over dq. So it's the Hamiltonian equal to P squared over 2 minus 2q cubed minus tq. Since it's non-autonomous, so the Hamiltonian is not a conserved quantity for this equation. It satisfies itself second order differential equation. And so actually I introduced this Hamiltonian as an excuse to introduce yet another quantity that I really need, which is the Painlevé one tau function. So the tau function is defined in this way. So its logarithmic derivative with respect to time is equal to the Hamiltonian. And so one of the nice things about the tau function is that unlike the Painlevé one transcendent itself, it is holomorphic in the entire complex plane. Holomorphic in C, and the zero locus of tau is exactly the polar locus of Q. So as T goes to the position of a movable double pole of Q, the tau function has a zero. So you have here the second integration constant, and the low order terms. Okay, so also I have to note already at this point that of course we can multiply the tau function by a constant because of its very definition, and later on we will talk about appropriate ways to fix this constant. The third thing we need to know about P1 is that it is related to isomonodromy. So Painlevé 1 describes the isomonodromic deformations so monodromy preserving deformations of a system of the form d phi over dz equal to a of z phi, where so a of z is a 2x2 matrix. It has just one pole on the Riemann sphere. One pole, better to say AZ dz, has one third order pole on CP1, and like the most singular contribution of this pole to A is non-diagonalizable. And so now if you use projective transformations to put this pole at infinity, you can actually parameterize A of z in the following way. So I will not explain why I introduce these letters in the way I introduce them. But the important thing here is that, so if we want now to deform our system, if we want to construct a family of such systems sharing the same monodromy properties, then this P and Q will satisfy exactly these equations over here, where T, so the time, is appearing at this place. Okay. Now, let me say a few words about what these monodromy properties are. So first we have to introduce the formal solution of the system. So phi formal of z will have the form z to 1 over 4 over 2 z14 over 2, z2 minus 1/4 minus z2 minus 1/4. Then we have a holomorphic series in z minus 1/2 gk to z minus k over 2, and an exponential factor, so exponential to 4/5 of z to the power 5/2 plus t z to 1/2 sigma 3. So this is the Pauli matrix. So this is a formal solution, formal because the series is divergent, and this matrices GK, they can be recursively determined from the linear system itself. Now, the actual solution of this system can only be asymptotic to the formal solution inside certain Stokes sectors. So basically, I have to introduce. So I will try to draw this pentagon. Yeah. So we will have Stokes sectors. Do we have a color chalk? Okay. No, but it's not. Yeah, maybe. No, but we can do without color. So we have this overlapping Stokes sectors, like I can draw it like this. Another sector like this, and so on. And so the actual canonical solutions of these systems are uniquely determined by the requirement that phi k of z is asymptotic to the formal solution for z going to infinity in sector omega k. So I have not defined it, but you can guess more or less what it is. And of course, these different canonical solutions, they have to be related on the overlap, like in this region here. They have to be related by a formula like phi k plus 1 of z equal to phi k of z times sk, where this s are 2 by 2 matrices independent of z. So these are Stokes matrices which have the familiar triangular structure. So you have something like S 2k plus 1 is 1, 1, S 2k plus 1, S 2k is 1, S 2k 1 and 0. And so you have a cyclic relation satisfied by this Stokes matrices, which defines you the monodromy manifold for Painlevé 1. So you have S1, S2, S3, S4, S5 equal to I sigma 1 Pauli matrix. I do not want to explain the origin of this, but well, basically this is related to these funny powers of z here and the square root in the exponential. Okay. So if you write this relation explicitly, so you will find a certain algebraic relation satisfied by the Stokes coefficients. So the monodromy manifold for P1 is given by is given by the system of equations sk plus 3 equal to I times 1 plus sk plus 1 with k in z over 5z. Okay, so it's not obvious that the solution of this is actually 5 periodic, but it is. And so if you try to play with this relation,
are the coefficients appearing inside the matrix?
yes. So these S's are exactly the Stokes coefficients appearing in these matrices relating canonical solutions. And they constitute the monodromy data.
From this, 5-term relation immediately follows that the logarithm has.
Yes, if you know like cluster algebra stuff, it's like the simplest example probably. But
It's just from Gauss.
okay.
That's
Well,
very difficult.
right. And so what do you have to remember from this? Well, the first thing is that so the dimension of this monodromy manifold is equal to 2, which makes possible this isomonodromic deformation, right? Because here we have 3 parameters. We can deform one of them and try to adjust the 2 others to keep the monodromy fixed. Satisfying this relation, so actually you will get only 2. So if you want, I can.
Only 3 relations are on the top.
Well, if you want, this is infinite number of relations, but you will get that as.
Yeah. So you just have 5 parameters, yeah?
Yeah.
And so it means the 3 independent relations. So
Yeah. So, for example, if you suppose that S2, S3 is not equal to -1, to have a non-zero value over here, then you have S5 from this relation, but you also have S1, which is equal to something like I minus S3 over 1 plus S2, S3, and a similar formula for S4. Okay, so it's, yes.
You mentioned at the beginning there was a movable singularity T0. Is this something special happened at T equals to 0?
In here, at the level of formal solution, I don't know how to see the movable singularity. At least I have no immediate answer.
There's no obvious interpretation of T0.
In here, no.
No, I mean also well, or
Here, of course, here there is an interpretation. It's just if you want to rewrite your initial system as a second-order scalar equation, which you can always do. What you will get is a scalar equation which has this irregular singularity at infinity, but you will also have this fake apparent singularity at z equal to q.
And so how is that related to T0, the apparent singularity? So is it like the position, so when Q is equal to T0, the apparent singularity goes to infinity?
So when t goes to t0, then the apparent singularity goes away. Yeah.
It goes,
So basically, your potential, which had this fake pole, becomes just cubic oscillator potential.
what do you call by cluster algebra structure?
Well, this is a system of relations for A2, if I remember correctly. Maybe. Yeah.
Andrei, instead of I, Q, you immediately obtain cheaper combination. This is a Schiller space. But these are classical relations. This, yes. But if you put you are doing this algebra of Hooke.
Yeah, of course. And so ultimately, I can write what we really need from all of this. So we have this Riemann-Hilbert correspondence, which is a map between the space of solutions of P1 and this space M of monodromy data that I have just introduced. So, these two things are in bijection. So to any point in the space of monodromy data corresponds a solution of Painlevé 1 and vice versa. So this is very easy to prove. So really your function Q of t is, you can look at it as a function of t and two monodromy variables, for example, S2 and S3, which play the role of integration constants or conserved quantities for our differential equation. Moreover, now the factors of I will appear. So if you denote S2k, so I introduce instead of this S, the monodromy exponents in this way. So S2k is equal to I times exponential 2 pi I nu k. Okay. So this function Q of t and let's say nu and nu prime related to S2 and S3. So this function Q will be periodic in both of these exponents. So you have this relation nu prime and the same relation for nu prime. Okay, so now I would like to generalize this periodicity to the tau function case. So instead of working with these meromorphic functions, I want to have a nicer object.
And these mu's are functions of P and Q.
You can do, so basically it depends in which way you want to consider this map.
The T is the same, or
yeah, so you can consider this as a map for fixed T, yeah. So if you know T and you know monodromy, in principle, so this Riemann-Hilbert correspondence or inverse Riemann-Hilbert correspondence allows you to reconstruct the linear system having that monodromy. Okay, so now what about the tau function? So when we have this periodicity for Q, so in principle you can immediately write the Fourier expansion of this function in these variables. So I introduce this QMN of t exponential to 2 pi I m nu plus n nu prime. Then, so these QMN are very difficult to compute, as is the Painlevé transcendent itself, but still, so you can at least formally write it. And so now I want to generalize this Fourier series to the tau function case. And many of you already see, I think, where this is going. So because we know that like Painlevé tau functions tau functions have this, very often they have this type of representation. So tau function is equal to a sum of, let me write it like exponential of I n nu prime. And here I will put some function f of nu plus n and t. So I use the same variables as in P1, but you have analogs of this for all the other Painlevé equations. And so this function f, depending on the context, it coincides sometimes with like c equal to 1 Virasoro conformal blocks. Sometimes you can check that it coincides with partition functions of certain supersymmetric gauge series in the self-dual background, with topological recursion partition functions and so on. So basically, however, the structure of the tau function expansion is not at all obvious, like from the beginning. Okay. I mean, this formula needs an explanation.
By now you used only periodicity for what?
Okay, let me develop. So look at this formula here. Okay, if you have such a formula for Q, you will have the same type of formula for momentum. You will have the same type of formula for the Hamiltonian. And next, so you want to integrate, right, the Hamiltonian. And so, like being very optimistic and looking at this formula, you could expect not something like this, but rather something of the form. Okay, so let me write tau of t, or yeah, log tau of t would be equal to a sum with respect to m and n integers, and then some functions f mn of t here, exponential of I m nu plus I n nu prime with 2 pi i's.
That's just basically a Laurent expansion in terms of two and three, yeah?
Yes.
Nothing else.
Yeah, exactly. Nothing else. Yeah. But this does not imply this. Okay. Moreover, this is even contradictory to that. Because, so if you write this formula in the previous form, 2 pi I n nu prime, and here, so basically you have some infinite number of functions fn of t and nu. So you will have infinite number of functions which are periodic in nu. Instead of that, you have just one function which gets shifted by integers. So now, in order to convince you that this is not a pathology, but something that really happens, we can consider an example. So the example will be the theta function with characteristics. So you take, so let us define something like this. So theta of t, nu and nu prime will be the sum with respect to n of the exponential of 2 pi I nu plus n squared t plus 2 pi I n nu prime. Okay. So it's exactly like a theta function with characteristics, but now the characteristics are non-integer, non-half integer. And so what you see is that, so this guy is like obviously periodic with respect to nu prime. However, it is not, it is quasi-periodic with respect to nu. Minus 2 pi I nu prime, right? You just make the shift of the summation variable and you see this, right? No, nu prime, because nu plus 1 means that I now have to shift and, yeah. And so you see that this is like a prototype of the structure that we have over here. And actually, this is a particular case of a Painlevé tau function corresponding to the Picard solutions of Painlevé 6. And so now I want to prove this structure. So I want to understand this, I want to prove this in a rigorous way. No, not at all. We don't need this actually. So the key ingredient that we do need is called the extended Jimbo Miva Ueno differential. So what is that? It's one form which is supposed to give you the differential of the tau function, but not only with respect to time, but also with respect to monodromy. So let me start to write this differential. So first we have this time part from Jimbo, Miva, and Ueno. And then, like the monodromy part, there is a general way to construct it for any isomonodromic problem, basically. If you can find this in my paper with Alexander X and Andrei Prokhorov. But the case of Painlevé 1 is so simple that I can even do it on the blackboard. So basically, suppose that we now have some monodromy parameter m, right? So dm, and so we want to have here some coefficient a, and ultimately we want this form to be closed. So we want a relation like h m is equal to a t. And looking at the form of h, it is very easy to guess, or it is very easy to check at least, that one possibility for a is to put a equal to 1 over 5 for h m plus 3q t q m minus 2 q q t m. So if you fix a to be this, then automatically you have this this relation. So m is any parameter so far. I'm proposing to not to like to stick to this Stokes coefficients. I can take this m to be any parameter, any local coordinate on the space of monodromy data that I'm pleased with. And so now, if we have this, we can now put some index to m and add here b dm2, where m2 is some other monodromy parameter and b is equal to a with M1 replaced by M2. So fixing this form of omega, so you can compute its differential. So we have already announced that so the mixed derivatives with respect to t and m will cancel out. So the only thing that will remain is this monodromy, pure monodromy contribution. And moreover, if you look at the form of this A, you can easily understand that, for example, this term will not contribute because it will be symmetric with respect to M1 and M2. Likewise, a part of this term where you differentiate this guy with respect to M2 will not contribute, same here. So the only thing which will contribute to this coefficient will be the derivative of this with respect to M2 and the derivative of this with respect to M2. And so what you will get is basically you can recognize as being P M1 Q M2 minus P M1 Q M2, which is nothing that, yeah, maybe opposite, I'm not sure.
M1, M2.
Ah, yeah, okay, M2, M1. Okay, so I hope I get the signs right, but hopefully the idea is clear. And so the point is that now what we get is symplectic form relevant to our initial Hamiltonian form of Painlevé 6. And even though our system is non-autonomous, so this form is independent of time. And therefore, if I now say that M1 and M2, so if M1 and M2 are Darboux coordinates on my monodromy manifold, then, so this is dm1, dm2. Maybe I will introduce here some factor to make the things nicer. So then you see that it suffices to add to my initial omega the differential, so something like 2 pi I m2 dm1, and this will become a closed one form. So I can use it as a definition of my tau function on this extended space of time and monodromy data. But now we are already almost here, because so suppose that we take our tau function, we fix some normalization over here. So in principle, I could put here an arbitrary constant depending on nu and nu prime. And then I'm looking at what happens to this tau function when I change, say, nu to nu plus 1. So for example, when I do analytic continuation along the suitable contour to avoid eventual poles of Q of t. Then, so the tau function that you will get in the end, it can differ from the initial tau function only by a constant factor, because the logarithmic differential of both of them should give this HDT. Yeah. Yeah.
Does it mean that this bracket between P and Q looks like Wronskian? It is constant equal to 2 times pi.
Sorry, I have not understood the question. So
when you write d omega,
yeah,
you write this bracket p
Yeah.
And this bracket looks like Wronskian of PQ.
Yeah.
Does it mean that it is 2 times pi? 2 times pi i.
No. No.
Why?
I mean, why it would be?
Right. You wrote dm1 with dm2.
Sorry. So this is just a normalization that I choose for this M1 and M2. I want to have 2 pi I to make the things so that this M1 and M2, I could leave this like that if you want. No. So what is equal to 1 is this, right? dm1 or dm2. Yeah, so this is true, but
So it's 1.
well, no. Okay, this is 1, but this is not just Wronskian, right?
No, okay. Wronskian, I told you for this, it is wrong name, but question, P sub M1, Q sub M2 minus P sub M2 times Q sub M1 equal to 1.
Yeah, of course, yeah.
That was my stupid question.
Yeah. Mm-hmm. So where I was, yeah. So basically, I wanted to use this extended Jimbo-Miller-Ueno differential to compare two tau functions. So I write the d log of tau of t mu prime or mu plus 1 and mu prime over tau t. Let me put here m1 and m2 rather, and here m1 and m2. And so now if you look at this formula, so you see that so this is 0, and so basically this means that you can set this ratio to be 1. Okay. On the other hand, the extended differential of so now you change m2 plus 1 t m1 and m2. So here on the other hand you will have some remnant of this correction term. So this is basically the abstraction for the logarithm of the tau function of being periodic in m1 and in m2. Okay. So what we get here is well, exponential just 2 pi I dm1, right? And this means that this ratio is equal to the exponential of, well, 2 pi I m1. Okay, so this is exactly like in this theta function example from before. And so the conclusion is that so this that the structure of the tau function expansion that many of you are familiar with is not something specific to like CFT or gauge theory or whatever. So this is just a consequence of the fact that nu and nu prime in this formula are Darboux coordinates with respect to the standard Poisson structure on Painlevé 1 monodromy manifold. I mean, you could take any other coordinates on this monodromy manifold, you would still be able to write this kind of formula. But the question then is, which choices of these local coordinates would lead to interesting functions f. Okay, and it so happens that like this choice related to exponents of the Stokes coefficients, indeed, it gives rise to like gauge theory partition functions, topological recursion partition function, and like most recently, irregular conformal blocks in the Painlevé one case. Okay, so
Up to certain moment, you had total symmetry of M1 and M2, or new and new prime. And
yes, this is
sometimes somehow you break. I didn't get at which moment.
here, perhaps again, it is instructive to look at the theta function example. So remember, so
These characteristics are from the very beginning. They're not symmetrically common.
yeah, but you see, if instead of this guy, I would correct. So what I should do? So perhaps I need to multiply this function by something like 2 pi I new prime. Okay, so I correct the definition by some trivial factor. Then this guy will become periodic in nu, but aperiodic, quasi-periodic in nu prime. And you see this this quasi-periodicity, you can have it either in nu or nu prime or in both, but you cannot exclude it completely. So that's my point.
And by that you mean that it depends on particular normalization.
Yeah. So basically I can, for example, choose to hide the quasi-periodicity with respect to nu into this prefactor, but then I will lose the periodicity with respect to other variable. And as you know, like these different choices, they, like in the language of conformal blocks, they will give you conformal blocks in different channels, for instance. Yeah.
If you want to check this symmetry breaking, you see that the omega is absolutely symmetric, but it's not closed. And to make it closed, you need to make some choice.
Yeah. You have to make some choice over here. Mm-hmm. Okay. So now in the time which is left, not so much, but I would like to discuss briefly the relation between this isomorphic tau function for Painlevé 1 and irregular conformal blocks, which is a result of a recent work by Pogosyan and Pogosyan. I don't know if the two are related, but I strongly suspect so. But the useful starting point for that will be my favorite picture, which is due to Chekhov, Natsokka, and Rubtsov, where you have so this standard picture for Painlevé 6, where the solution is expressed in terms of where this function f appearing in the Fourier decomposition is related to this standard regular full-point Virasoro conformal block. And then, well, you have many errors. So you have this whole confluence diagram. So this is P5. Then you have P5 degenerate. And so the surfaces that appear here, they basically encode the information about this linear differential system. So here it has 4 simple poles, here it has 4 simple poles and 1 double pole, here 2 simple poles and 1 double pole with non-diagonalizable leading on the order contribution. So this is a so-called P5 degenerate. Then you have here Painlevé 3. So we are drawing this in order to not write the formulas. And here we have, so this is P3 of type D6. Here we have P3 of type D7. Then here we have this P3D8, the radial St. Gordon. And so this is the upper part of the confluence diagram. And like for all equations that you have here, you have some conformal block interpretation, which is related to this irregular conformal blocks that were introduced by Gayotto in 2009, I guess. And then a generalization was proposed by Giulio Katsunobu, Maruyoshi, and Tansini. But we have also this lower part of the confluence diagram, which is problematic, where you have Painlevé 4, so 1 simple pole and 1 triple pole in the linear system. Then here we have what? So we have this hexagon, which corresponds to one of the 2 Lax pairs of Painlevé 2. You have another Lax pair for Painlevé 2, which has this form here, so 3 cusps and 1 regular singularity. And finally, you have like the most degenerate picture is P1. So 1 singularity, 5 cusps, corresponding to this 3rd order pole with non-diagonalizable coefficient. Yeah.
So this extended Chimbo-Newell differential, so is it useful to kind of argue that you have this particular form of the graph function?
This is my point.
But suppose that I want to, so in the case of Painlevé 1, let's take Painlevé 3. You have, like, you can expand the graph function on 0 infinity. And then you have this connection coefficient in some sense, which
Yeah.
So is this formalism which use this extended Chimbo-Newell differential also useful to determine C?
To the C? What do you mean?
So the coefficient which relate in some sense the tau function at 0 and at infinity.
Yes. So this is the like the principal ingredient that we used to obtain it for some equations like P6 and P2, but in principle you can do it for all equations. Yeah.
But in your
Yeah. So there is this error here as well. But what I want to stress maybe is that so irrespectively of CFT or gauge theory, I can write this formula for any Painlevé and for any actually isomonodromic tau function, even if you have like multi-point conformal block, right? So it automatically follows from this extended differential. And notice that in this case, so these f's, they are actual functions. So they are not asymptotic series of something which accidentally coincides with asymptotic series for like, topological recursion partition function, for example. No, these are true functions that you can compute from this solution of the differential equation. Moreover, you can just use the differential equation to compute, to generate the asymptotic expansion of this guy. Okay, so I have to wrap up quickly. So maybe I will not be able to say everything that I wanted. So let me just say the following. So the conformal blocks which are relevant to the tau function appearing in the upper half, they involve Whittaker states diagonalizing the L1 and L2 generators of Virasoro algebra and killed by all Ln's with n greater than 2. Okay. So, for example, this conformal block over here, it will be something like, so you have a vertex operator, delta 1, whatever, lambda 1, lambda 2. So this is the function which will appear here, and the same type of construction is valid for the other equations here. Now, in the conformal blocks for the bottom part of the confluence diagram are much more tricky to construct. Why? Because well, one thing that you can think of if you want to consider higher order poles is to consider Whittaker states of rank R which share the similar property. So they are they give eigenvalues. So they are joint eigenstates of Ln's for n from R to R, killed by all the other positive Ln's. But here immediately we face a problem when we try to write an expression like this expression here, because we don't have any canonical pairing between the Whittaker module generated by this vector and highest weight module. So basically, when I write something of this form, L1 to the power k, lambda 2, lambda 3, lambda 4, so I cannot express any of such 3-point functions in terms of just scalar product of the highest weight and Whittaker state. Okay, and this is a problem. Now there is a paper by Gayotto and Teschner where they have fixed this problem by generalizing or making maybe more precise the action of the Virasoro algebra on the Whittaker state. So basically, I have to supplement these relations that I have over here by something of this form. So for n from 0 to r minus 1, so the action of this on the Whittaker state is given by a differential operator of first order. So lambda Ln R, lambda R, lambda 2R.
It's like action of L naught in the uppercase.
What is
L naught.
Well, a naught in the upper case acts just by eigenvalue. Yeah. In this case. Yeah. So
there, somehow there it appears automatically. Here you say that you have to add this as a certain condition.
No, there I would say that so this derivative representation of L naught is our way to fix the normalization of this Whittaker state. I can explain to you later if you want. But yes, in principle, this is very similar to that. And the expressions of these differential operators. So basically, what I'm talking about is an anti-homomorphism from the positive part of the Virasoro algebra into the algebra of differential operators. Okay, so the explicit expressions for these LNs, they come from Bosonization. But once you have guessed them from Bosonization, you can forget about this Feigen-Fuchs formula and just use it and compute the corresponding conformal block. And it so happens that, for example, the conformal block relevant for P2 is nothing but this type of product. But you still, so I3 is an analog of this. So if you want lambda 2, lambda 3, lambda 5, lambda 6, lambda 6. No, lambda 4, lambda 5, lambda 6. Okay, but you still had, so Gayotta and Teschner, this is 2012, I guess, but you still have a problem with half integer ranks, which you need for P1. And so very recently there was this paper by Pogosyan and Pogosyan that I have mentioned, which solves which generalizes the construction of Gayotta and Teschner to the rank 5 half. So basically, where you don't have this. So the problem is that in this case, the Bosonization formulas do not work. So you have to guess what will be the this realization of positive Virasoro in the algebra of differential operators. But once you have guessed the expressions, you can just follow the recipe of Gayotta and Teschner and end up with an expression with a way to compute, I would rather say, the conformal block given the Painlevé-Van't function. So now I think I have to stop. I'm over time. So if you are interested to know more, don't hesitate to ask me. Yeah, thank you.
Any questions, comments?
Yeah, so these conform blocks will be dependent on this T parameter, which you introduced.
Yeah.
That's basically the position of some operator insertion.
So this is actually the delicate point, because you see, for example, like here, whenever you have a regular singular point, indeed you have something like a point of its insertion of a vertex operator. This is no longer the case in here in Painlevé-1 and Painlevé-2. So you have no vertex operators there, only irregular states.
Right. Those are fixed at some point. Yeah. At infinity, say.
Yeah. For example.
But my question is the following: before you started with this equation, which was z-dependent, and we considered the isomonotropy of that one, is there an interpretation of that z parameter for
It's
in terms of positions or anything?
Yeah, it's a degenerate field that you add to your conformal block.
But it's it is well. So it's basically the position of another field.
Yeah, yeah, yeah.
But these things will depend on Z as well.
Yeah, so if you put in here something like phi 1, 2 of Z, so you can build the fundamental matrix solutions out of these quantities.
So these points, these regular singular points, which are still free, they are T or Z dependent. Those are T dependent.
No, these are T. So this is like infinity, infinity, 1, T, and
But
0.
if you have, let's say, more than that, then there will be, that's the Z parameter. If you have some degenerate field.
Yeah. Then I would need to draw more. Yeah.
Can you classify ambiguities in the construction of the regular states? I mean, the way in which you solve those normalization problems, or is there kind of
Well, in this rank 2 case, this is basically the ambiguity. But you see already here you have like an infinite number of parameters that you have to fix. Now, if you would have like rank 3 state, then so starting from lambda 3, so then you would also have here something like L2 to the power L, and so on. I don't know if this answers your question or.
no? I mean, the way in which you parameterize these irregular states, whether then
Whether I can from.
you will have your material expression for the function in the end.
Mm-hmm.
So, if there is a way to understand the choice of polarization, the action of you have a choice of polarization when you choose the monoid parameters, and here a choice of parameterization of the solution of the regular state for to build the regular problem.
Yeah, so actually this is what I wanted.
An action of the change of frame, let's say, in the monoid parameters, in a change of the way of solving the irregular state.
Um, I'm afraid I don't have a good answer, so probably I will try to discuss with you after. Yeah, I do have some, but yeah.
Related question to this, maybe rephrased. I mean, how much rigid is the constructor of these irregular states in the sense in representation theory? Can you show that you have?
No. Mathematically, so this everything is conjecture there. So basically, what you do is the following. So you say that the irregular state of rank R is some function of, let's say, this Bosonization parameters or eigenvalues, if you want, f of lambda. And then you have irregular state of rank R minus 1 plus a series in lambda to R, so the highest eigenvalue, lambda to R to the power k, I k R minus 1. Okay, so this is the what you want, what you ask for, and then the statement is, which is basically a conjecture, is that like the consistency with the Virasoro algebra fixes both this non-analytic prefactor and all of the generalized descendants which appear in here. But even like in rank 2 case, which was considered by Gayot and Teschner, even in that case, this is not a theorem. This is just, you do computation order by order, and it seems like the solution is unique indeed. But there is no proof of that. And this is the best that we have so far.
General question about this conformal block or just expansion.
So what is the property of the f function that reflects the Painlevé property of the initial solution?
Analyticity. So, for example, like in the Painlevé 6 case, so the tau function will be analytic convergent power series in the unit disk, and this is what we expect from conformal.
So you said like to get these Whittaker vectors, you need to use a special choice of the book coordinates, which are the Stokes constants, right? I mean, to expand the tau function, you have to choose our book coordinates, and the good choice that gives you Whittaker vectors is the Stokes constant. But then you also said that you have 5 of them, only 2 are independent. You could pick any 2.
Yeah.
Is the statement that, so first of all, the tau function is going to jump, right, if you choose different pairs?
I would say it differently. So suppose I have fixed a pair like this, nu1 and nu2. So then I have this conformal, would be conformal block function, which is unambiguously defined by tau. And the statement is that this function has a nice asymptotic expansion along a certain direction at infinity in the t-plane. Like so, this nu1 and nu2 corresponds to t goes to minus infinity, if I remember. Now, if instead of that you chose nu2 and nu3, so you would get a different function which would have a nice asymptotic expansion as t goes to minus exponential 2 pi I over 5 infinity.
Would these f's be related? So if you expand tau function in different choice of the book coordinates, still using the Stokes constant?
They would be related, but they would not be the same.
Just rotate the t in the t-plane by 2 pi over 5.
I would rather say that their asymptotic expansions would be related just by the rotation. Yeah.
But those Stokes matrices before, those were in the Z plane again.
Yeah. So here we are talking about a kind of nonlinear Stokes phenomenon. So the analog, so you still have this change when you go from one ray to another in the t plane, but well, the change is nonlinear for the tau function.
And the transition function for tau is always this canonical.
Yeah.
Of the canonical.
Yeah.
It also has an expansion as t goes to 0, or that's
for Painlevé 1, it's not a special point.
So these 5 representatives, say, of the pi, they should arrive from 5 in equivalent ways of solving the irregular state.
Yeah, they are inequivalent, but only up to change of variables.
Any more questions? Okay, if not, let's thank Oleg again.